Good morning, everyone. I'm Chadu, scientist from Singapore Institute of Manufacturing Technology. Today, I'm going to present on the topic 4D printed lightweight foaming polylactic acid and going to discuss about the process, structure, and shape and the relationship. The outline of my presentation is starting with the background of polylactic acid and explaining about the objective and methodology of our research work and initial characterization, followed by microstructural and shape memory analysis, and I'm concluding the presentation of the discussion and conclusion. Well-studied shape memory polymer and different complex shapes has been achieved by altering the printing process and the programming after printing. With different infill pad, with the different fillers, we can able to enhance the mechanical performance and the electrical conductivity of polylactic acid. But there are lack of comprehensive study on the shape memory performance of the foaming PLA. And also there is a lack of detailed relationship between the printing process, microstructure, and shape memory performance. With this background, our research objective is to understand the relationship between the printing process, microstructure, and the shape memory effect of printed lightweight polylactic acid, through which we can tailor the printed parts performance and we can able to control the process parameter to control the shape memory performance. So now what is this foaming lightweight PLA? So the foaming additives are added into the PLA. At higher extrusion temperature, the foaming additives are activated, through which the microstructure of the PLA is controlled or altered, through which the density and overall weight of the structure has been altered. So now our research methodology is altering the process parameter, controlling the process parameter to have different microstructure and to see how these microstructures are affecting the shape memory property of the lightweight polylactic acid. As a first step, we studied the shape memory property. We studied the thermal properties of the lightweight PLA and compared with the neat PLA filament, through which we understood that the degradation temperature of the polylactic acid is lower than that of the neat PLA filament. So through which we control the process window to print the lightweight polylactic acid. As I said earlier, the extrusion temperature is affecting the microstructure and through which the density is varied. So we understood the effect of extrusion temperature on the density by printing single wall perimeter test cubes with the different process parameters starting from 200 degrees Celsius to 228. And we analyzed the density of the sample and we could see the foaming alter the density at 228, we could see maximum foaming and the decrease in the density and also increase in the wall thickness with the increase in the temperature. So to understand further how this extrusion temperature is actually affecting the foaming process, so the single wall perimeter cubes were observed under microscopy for the foaming pattern or the foaming pattern. So we could see the increase in percentage of foaming from the lower extrusion temperature to higher extrusion temperature. And it is very visible in a micrograph that the particles are formed when we see the sample printed at 228 degrees Celsius. With the initial characterization and the initial experiments, so we have used two extrusion temperatures at 200 degrees Celsius and 228 degrees Celsius with the three different infill angles, 0, 45, and 90. We should choose these process parameter to study the shape memory effect of lightweight PLA. So overall, we said the samples printed 200 is unformed samples and sample printed at 228 is formed sample. So to study the combination of process parameter, that the extrusion temperature and the infill angles, we have selected a flat sample and we observe the microstructure of the flat sample and the shape memory effect. So this is a cross-section ACM images of the sample printed at 200 and 228. So it is very evident that the extrusion temperature affect the microstructural morphology. And you can see the porous cluster of pores because of the foaming. You can see the foamed structure for the foamed samples, which shows that the extrusion temperature affecting the microstructure of the polymer. Here, also at a higher magnification, we could see two sets of pore. One is micropores and nanopores. The average size of pores for the foam sample is around 447 micrometer, and the minimum pore, the other small pore size is 846 nanometer, through which we understood that the porous structures are affected by the extrusion temperature, and different pores has been obtained with the extrusion temperature. So we are following that, we did this shape memory analysis for the samples printed. These are the sample printed. So here we describe the shape memory analysis with two stages. Stage 1 is a release of residual stress, and the stage 2 is a programming after printing. That is the loading and unloading, unloading or recovery stage. The samples printed with the different extrusion temperature, with the different infill pattern, will undergo stage 1 shape memory affect the release of residual stress, and the average of the residual stress release has been plotted here, where you could see the infill pattern and the extrusion temperature has a combined effect on the release of residual stress. In case of residual stress, the samples undergone stage 2, the programming step, the stage 2 release of stage 2 shape memory process. So here we heat the sample, and then we will, with the higher temperature, we will load the sample to give a temporary shape. Again, the samples are heated, where it will recover to the original shape. So this one single step is called as the shape memory cycle, and we have performed the 10 shape memory cycle for each sample. So the average recovery time for each sample printed at different infill pattern and extrusion temperature plotted here. From this, we can see a pattern that there is a decrease in the recovery time for both the sample, for the formed and unformed sample. And we could see there is a longer recovery time for the formed sample. So through which also we concluded that there is a combined effect of infill pattern and extrusion temperature on the recovery time. Coming to the shape-shifting mechanism, so we obtained bending for the samples printed at 0-degree infill pattern, 90-degree infill pattern, and we obtained twisting for the sample printed at 45-degree. This is consistent for the both extrusion temperature for the formed and the unformed samples. And this is in line with the literature due to the expansion and shrinkage of PLA. And also the bending angle differs with for each process parameter combination. For each extrusion temperature and combination of infill pattern, we obtain different bending angle as plotted in the graph. So from this, we could say that the bending angle, the infill pattern and the extrusion temperature is affecting the bending angle. So there is, and the recovery time and the bending angle. So the bending angle is different for 0-degree infill pattern and different for 45 and 90. So one possible discussion for the increase or the longer recovery time for the formed particle, the formed sample, is due to the coefficient of thermal expansion. So we analyzed the lightweight PLA with the thermomechanical analysis. So for the formed and unformed samples, you could see from the graph that the formed sample is having lower CTE than the unformed samples. So this may be due to the pore structure act like a insulator, which actually decreases the coefficient of thermal expansion, and which affect the time of recovery as well as the recovery strain of the lightweight PLA. So overall, from the shape memory effect, we could understand the residual stresses is affected by the infill pattern and the extrusion temperature, and the release of residual stress is always towards curved up the print direction of the part. And the response time decreases with the number of cycle. For the response time for the first cycle is fast, which is less than 1 second, and the response time for the 10 cycles is slow, which is nearly equal to 3 seconds. So we can say that the response time, the actuation time, and the extent of motion depend upon the number of cycle as well as the deformed curvature of the sample. So overall, from our research, we could conclude that for the same material, the same process, by altering the extrusion temperature, we are obtaining different microstructural morphology, which is actually affecting the density of the part and the coefficient of thermal expansion, Combining it with a different infill pattern, we are obtaining different shape shifting mechanism and different bending angle through which the overall shape memory effect, overall it affects the shape memory effect of the lightweight PLA. So through this, through understanding the relationship of the microstructure, process parameter, we could able to print a simple structure or same structure with a different shape memory performance. Further, our future work is to further understand the porous morphology and the after number of shape memory cycle and fatigue behavior of the sample in the mechanical and the mechanical analysis of the formed and unformed samples. Thank you for the attention, and I would like to thank my 4D printing team for the support.